In this video, we're going to discuss compositions of trigonometric and inverse trigonometric functions. In particular, we're going to evaluate expressions that involve compositions of the various trigonometric functions and their own inverses, such as the arc sine of an angle, and we're going to use right triangles to evaluate expressions involving trigonometric functions and the inverse functions of other trigonometric functions, such as the sine of the inverse tangent of some value. We'll first look at a couple examples where we're composing a trig function with its own inverse trig function. For example, composing the sine function with the inverse sine function, as in this example. Here we want to evaluate these two expressions, the inverse sine of pi over 3 and the inverse sine of 2 pi over 3. Typically, when we compose a function and its inverse function, we get the exact same value that we started with back. However, because of the way the inverse trig functions are defined, and in particular the way the ranges of the inverse trig functions are defined, we need to evaluate these types of compositions with care. Sometimes we will get the correct angle back, and sometimes we won't. The easiest way to approach these is to simply evaluate the trig function first, and then compute the inverse trig function of that ratio. For example, in our first one, we have inside the inverse trig function the sine of pi over 3. The sine of pi over 3 is known to be square root of 3 over 2, and so we need to compute the inverse sine of the square root of 3 over 2. Here we want an angle whose sine value is square root of 3 over 2 and lies between negative pi over 2 and positive pi over 2, and that angle is indeed pi over 3. So in this case, we do get exactly the angle that we had started with inside the trig function. We get the same angle back. But as we'll see here in the second example, that is not always the case. If we apply the same reasoning to the second example, we first compute the sine of 2 pi over 3, and we know that the reference angle for 2 pi over 3 is pi over 3, and we just saw that the sine of that is square root of 3 over 2. This is an angle in quadrant 2, and so therefore the sine is positive. So the sine of 2 pi over 3 is also the square root of 3 over 2. And so what we have to compute here in this example as well is the inverse sine of square root of 3 over 2, which is exactly what we just computed in the first part, and this is pi over 3. So notice that this is not the same as the angle that we started with. So here we composed a function and its inverse function, and we did not get the angle that we started with. The reason is that 2 pi over 3 is not between negative pi over 2 and pi over 2, and so it's not in the correct range for the inverse sine function. This is why we need to be very careful when evaluating compositions of a trig function with its inverse. Sometimes it will be the angle that we start with, as in the first case here, and other times it will not be. Let's look at a similar example involving cosine and inverse cosine. So here we want to evaluate the inverse cosine of 2 pi over 3 and the inverse cosine of negative pi over 3. Again, we'll observe that sometimes we get the original angle back and sometimes we do not. In the first example, we'll start by evaluating cosine of 2 pi over 3. And cosine of 2 pi over 3 is going to be negative 1/2. We know the reference angle of that angle is pi over 3, and that cosine of pi over 3 is 1/2. And since we're in the second quadrant with the 2 pi over 3 angle, we have a negative cosine value, so the cosine is negative 1/2. So we want to compute the inverse cosine of negative 1/2. This means we want the angle between 0 and pi radians, whose cosine is negative 1/2. And because 2 pi over 3 fits that range, it's between 0 and pi radians, we get an exact value of 2 pi over 3, which is indeed what we started with, that same angle. So we get the same angle back when we compose the cosine and inverse cosine functions for this particular angle. Note that this is because 2 pi over 3 lies in the range of the inverse cosine function, 0 to pi. In our second example, we'll first start by computing the cosine of negative pi over 3. When we know the cosine of pi over 3 is 1/2, and negative pi over 3 is an angle in the fourth quadrant. We get it by rotating pi over 3 radians in the clockwise direction. In the fourth quadrant, the cosine is positive, and so our cosine of negative pi over 3 is 1/2. So what we really need to compute here is the inverse cosine of positive 1/2. We need to find an angle whose cosine is 1/2 and lies between 0 and pi radians, and that angle is pi over 3. And so the inverse cosine of negative pi over 3 is equal to pi over 3. Again, like in the example of the sines, notice that in this case we do not get the angle that we started with back. This is because negative pi over 3 does not lie in the range for the inverse cosine, which is 0 to pi. Whereas in the first example, 2 pi over 3 does land in that range. In this example, we're going to evaluate the composition of a trig function and a different inverse trig function. Specifically, we're going to evaluate the arcsine, or inverse sine, of the cosine of 13 pi over 6. The first thing that we should notice here is that the angle 13 pi over 6 is actually bigger than a complete rotation. We can think of this as 12 pi over 6 plus pi over 6. And 12 pi over 6, of course, is 2 pi. And so our angle, 13 pi over 6 and pi over 6, differ by a multiple of 2 pi, which means they're coterminal angles. And since they're coterminal angles, what we know is that their sine and cosine values are all the same. So the arcsine of cosine of 13 pi over 6 is the same as the arcsine of the cosine of pi over 6. So here we're just using the fact that these two angles are coterminal, and therefore their cosine values are equal. And now we can compute this just as in the previous example. We just have to be sure that we notice that the trig function and inverse trig function are different. But we first want to compute the cosine of pi over 6, and this is one that we should know. It is square root of 3 over 2. And so what we really want to compute here is the arcsine of square root of 3 over 2. So we need an angle whose sine is that value, and the angle in the first quadrant whose sine is square root of 3 over 2 is pi over 3. And so that is the value of this expression in this example. In this example, we want to find the exact value for the sine of the inverse cosine of 4/5. This is again a composition of a trig function and an inverse trig function, but notice that it's different than the ones we've previously seen. All of the previous examples have had the standard trig function evaluated first, and then the inverse trig function evaluated at that particular value. And here, those roles are reversed. We're first going to evaluate the inverse trig function, in this case the inverse cosine of 4/5, and then evaluate the sine function of that afterwards. In order to do this, we can use a couple different approaches. The easiest way, regardless of which trig functions or inverse trig functions appear, is to use a right triangle. In order to do that, what we need to remember is that the inverse cosine of 4/5 is an angle. This is always the case. Any inverse trig function of a number will always be an angle. And so let's give this angle a name, and let's call it theta, as we standardly do. And so if I have a right triangle here that I'll make with angle theta involved, maybe here's angle theta, there's the right angle. We know from this expression that if theta is the inverse cosine of 4/5, that this means that the cosine of theta is equal to 4/5. So in our right triangle, we can identify two of the sides of the triangle. We could identify the adjacent side of angle theta as length 4 and the hypotenuse as length 5. And when we do that, we can then use the Pythagorean theorem to find the length of the third side. In this case, it's probably obvious what that is, but just in case it's not, we could always use the Pythagorean theorem. X squared plus 4 squared equals 5 squared in this case. Remember, the hypotenuse squared should always be on the side by itself. And this is x squared plus 16 equals 25. We can subtract 16 to get x squared equals 9. And then when we take the square root of both sides, we do need to remember that in general, we have a plus or minus involved when we take the square roots of both sides of an equation. But really, we're just looking for a positive one here because we want a distance. And so our third side is a 3. So this is the standard 3, 4, 5 right triangle. Right. Now that we have all three sides, we can easily compute the value that we want. Right. We wanted to find sine of inverse cosine of 4/5. Well, this is just the sine of angle theta. We defined theta to be that angle inverse cosine of 4/5. And from this triangle, the sine is going to be 3/5, the opposite side, over the hypotenuse, which is 3 over 5. And so our sine of inverse cosine of 4/5 is equal to 3/5. Our last example here, we want to find an exact value for the sine of the inverse tangent of negative 7/4. And we're going to follow a very similar strategy to the previous example, although we have to pay attention to one small detail. In particular, that the value of the tangent here is going to be a negative number, negative 7/4. So following along like the previous example, we're going to let theta be this angle, the inverse tangent of negative 7/4. And we know that that means that the tangent of theta will be equal to negative 7 over 4. The fact that this angle is negative tells us that we are going to have an angle in quadrant 4. The inverse tangent function gives us an angle theta, which is between negative pi over 2 and positive pi over 2, which means that we're in quadrants 4 or 1. And because the tangent is a negative value here, we're going to have to be in quadrant 4, since in quadrant 1, the tangent is positive. And so just to make sure that we remember this, because this might play a role in our final answer, we're going to draw a right triangle that happens to be in the 4th quadrant. And this will be our angle theta here. Just like in the last example, we'll now use the fact that the tangent is negative 7 over 4 by having an opposite side of length 7 and an adjacent side of length 4. We want to find the value of the hypotenuse here, and we can use the Pythagorean theorem. Right, so we know that 4 squared plus 7 squared will equal the hypotenuse squared. This would be 16 plus 49 is equal to the hypotenuse squared. And this looks like 65 will be the hypotenuse squared. And therefore, taking square roots of both sides and excluding the negative because we want a distance here, it looks like our hypotenuse will be the square root of 65. And so now that we have all three of our side lengths, we can compute any trig function that we want of this particular triangle. So we have sine of inverse tangent of negative 7/4. We know that that is going to be equal to the sine of theta, because we define theta to be that angle inside the sine function. And now we just use our triangle to find the sine of this angle. And so the sine is, of course, the opposite over the hypotenuse, so 7 over square root 65. However, we do need to remember that we are in quadrant 4. And in quadrant 4, the sine is negative. And so we do have to account for that by making this a negative 7 over square root 65. The only reason we know to make this a negative is the fact that the tangent of this angle is a negative value, which tells us that we're in quadrant 4. In the previous example, we didn't discuss this because the angle there was an acute angle in quadrant 1, and all trig functions are positive in quadrant 1, so this was nothing to worry about. However, in this case, we do have to worry and take account of the negative sign to make sure that we're giving the appropriate positive or negative sign for our trig function. In this case, because we're in quadrant 4 and that we're evaluating a sine function, we should have a negative value as our answer.